Greetings. Welcome to Intel Innovations. My name is Devendra Das Sarma. Chris and I are excited to participate and talk about Compute Express Link, driving innovations in compute platforms. We hope everyone is staying safe and healthy. Here is the agenda for today. We will talk about Compute Express Link, CXL, and its evolution. Then we will delve into the usage models enabled by CXL. We will specifically discuss how memory challenges in the compute infrastructure is addressed by CXL, along with a cool demo of a CXL-based system. In the true spirit of Intel innovation, we will talk about the types of innovation that CXL will unleash. Finally, we will conclude. When we look at the industry landscape today, we see some clear megatrends emerge. Cloud computing has become ubiquitous. Networking and edge computing are exploding and increasingly using the cloud infrastructure. Artificial intelligence and analytics to process the data is driving a lot of innovations across the board. All of these are driving the demand for faster data processing. We see increasing demand for heterogeneous processing as people want to deploy different types of compute for different applications, whether it is general purpose CPUs, GPGPUs, custom ASIC, or FPGA. Each is important and best suited to solve some class of problems. We also see the need for increased memory capacity and bandwidth in platforms. Significant technical innovations in storage class memories have resulted in those memories approaching DRAM-like latency and bandwidth with non-volatile characteristics such as our 3D crosspoint. The megatrends that we are discussing here take advantage of these types of memory in addition to the evolution of the traditional DRAM memory and storage. Compute Express Link is defined ground up to address the challenges in the evolving landscape by making both heterogeneous computing as well as different types of memory efficient and sustain the needs of the compute segment for many years to come. The picture on the left here shows the system view with PCI Express only. Memory attached to the CPU, such as DRAM, can be mapped as coherent memory. Data consistency there is guaranteed by hardware cache coherency protocols. Memory attached to a PCI Express device, if there is any, it is also mapped into the system memory space, but it is mapped as memory mapped IO and hence is uncacheable. So the memory that is attached to the CPU is different in its semantics than the memory that is attached to a PCI Express device today. So when a CPU wants to access the DRAM memory, it uses caching to access the data. Whereas if you wants to access the memory that is attached to the DRAM to the PCI Express device, it has to go to the device for every single access. Similarly, for a PCI Express device accessing the system memory, it does what is known as a direct memory access, where the root port performs the protocol translation between the IO world and the coherency world, as the IO device has the producer-consumer semantics, which is different than the cache coherency semantics. The producer-consumer model works really well for a wide range of IO devices, especially when performing bulk transfers, such as those involved with traditional storage or moving data in and out across a networking interface. We definitely want to preserve those usages. However, for accelerators that want to work on a fine-grained sharing of data with the processor, the PCI Express mechanism needs to be augmented with enhancements that is shown on the second diagram on the right. We want to have the device be able to cache memory as shown as memory load store. That way, the devices do not need to DMA all of the data in and out of memory when the data needs to move between the CPU and the device or between devices. Now, similarly, the memory that is attached to the device can be mapped to the system memory as cacheable or write-back memory. This can be used for memory expansion or even map the device memory into the system space for more efficient access. With CXL, we enable heterogeneous computing and disaggregation. Memory resources anywhere in the system can be shared efficiently between these computing elements due to the memory and coherency semantics. This results in enhanced movement of operands and results. Further, we can use CXL for memory bandwidth and capacity expansion, supporting memory tiering across different memory types. Compute Express Link runs on PCI Express infrastructure and leverages PCI Express. So what you have here is a CPU which has got both the PCI Express as well as Compute Express Link or CXL infrastructure. On the slot, which is a PCI Express slot, you could plug in either a PCI Express device or a CXL device. It's full plug and play. Very early on in the link training, the link understands what type of device is plugged in and turns on the appropriate characteristics. The widths that are supported for CXL are by 4, by 8, and by 16. And the data rate that is supported by CXL is 32 gig, although we can fall back in speeds to 8 gig and 16 gig. We fundamentally take full advantage of the PCI Express infrastructure, add coherency and memory semantics on top of that. Compute Express Link is defined ground up to address the challenges in the evolving compute landscape by making both heterogeneous computing as well as different types of memory efficient. It's built on PCIe infrastructure, overlays caching protocol, memory protocol. So you got 3 protocols, CXL.io, which is the IO part of the stack, identical to PCI Express. It is used for things like device discovery, configuration, register access, interrupts, virtualization, and most importantly, the bulk DMA with producer-consumer semantics. CXL.io is mandatory for CXL. CXL.cache protocol is optional for a device. It allows a device to cache the system memory in a coherent and low latency manner. CXL.memory protocol is also optional for the device. It allows the processor as well as other CXL devices in the system to be able to cache the memory that is attached to the device in a coherent manner. Latency is a critical component to ensure system performance with CXL. We are expecting latencies for CXL.cache and CXL.mem in the range of symmetric cache coherency links like our Ultra Path Interconnect or UPI. For a CPU load to use latency, we expect it to be significantly less than 200 nanosecond, which would be significantly less than half of a comparable PCI Express access. CXL is an asymmetric protocol. Thus, the protocol flows and message classes are different between the host processor and the devices. That's a conscious decision to keep the protocol simple and the implementation easy for the devices. Host processors have their proprietary home agent functionality, which orchestrates cache coherency in the system. Home agent functionality is very dependent on the underlying microarchitecture. So CXL just abstracts away the caching functionality through a simple set of commands that conform to the messy, modified, shared, exclusive, invalid messy protocol. And it also does the same thing on the CXL.memory side, where it provides a simple set of memory commands along with the ability to store some metadata like the directory bits. This way, memory devices don't really need to understand the coherency flows, and this asymmetry has fundamentally helped us ensure backward compatibility without stifling performance or without stifling innovations. CXL specification is defined ground up to be low latency for cache and memory accesses, which are uber latency sensitive. And that's the reason why we are multiplexing these protocols at the file layer level with a fixed size of 66 byte of FLIT, which is optimized for cache line accesses. It's 64 bytes of data and then 2 bytes for the CRC. Again, the goal is to reach UPI style latency in these links for caching and memory semantics. Now let's talk about the usage models that are enabled by CXL. Here are some of the typical usage models that are targeted by CXL 1.0 and 1.1. There are 3 types of devices, namely type 1, type 2, and type 3 devices, as shown in the picture here from left to right. An example of a type 1 device would be a SmartNIC or an accelerator. It uses I/O and caching semantics. I/O is used for bulk transfers, and caching is used for things such as advanced atomic support or things like PGAS, partition global address space, ordering enforcement. In the PGAS model, instead of waiting for a read completion before launching a subsequent write on the I/O side with PCI Express, the smart NIC could prefetch those cache lines out of order, but complete them in the local cache in order, delivering much better bandwidth. Type 2 examples are GPGPU and dense computation, where all three protocols are used. Here, the accelerators and host processors work closely. There is no need to hand off entire data structure and the results. Only those that will be cached will be used using the cache coherency mechanism, and cache coherency will be there to ensure global visibility. Last but not the least is the memory buffers. And Chris will talk more about that. SerDes is fundamentally more bandwidth efficient per pin. So CXL can be used for memory bandwidth and memory capacity expansion. It also enables heterogeneous memory, including persistent memory support, and also support multiple memory hierarchies since the memory controller is on the device side. There is also something of importance here where a type 2 can be deployed in some of the traditional memory devices, which can offer even more compelling value propositions that we will see later. Now let's look into what CXL 2.0 enables. CXL 2.0 is fully backwards compatible with CXL 1.0 and 1.1. CXL 1.0, 1.1 was based on a single node. What CXL 2.0 does is it enables resources to be pooled across multiple nodes. So essentially, CXL 2.0 enables one to move from a drawer level to a sub-rack or a rack level in the data center. In the diagram, you have multiple hosts that have accesses to multiple devices. The assignment of devices to the hosts can change over time depending on the demand, following the hot plug flows that are defined in CXL 2.0 specification. CXL 2.0 also specifies a standardized fabric manager to orchestrate resource allocation across multiple hosts. Each host can have its own dedicated resources plus access to those in the pooled resources. So that way you can have fungible set of resources across multiple hosts. CXL 2.0 further expands to define memory devices that can be simultaneously pooled across multiple hosts, as shown in the picture there. This allows for partial allocation of devices to the host, and the number of hosts by themselves can also change over time. In addition to all of this, CXL 2.0 also architects the persistence flows, which is done to work seamlessly with fabrics. It also defines software API for devices to enable system software to manage the devices. We have done security enhancements on top of the device TLB that existed with CXL 1.0. Things like device authentication, link encryption, security through the switches. In short, CXL 2.0 and beyond is going to be a game changer for the industry. It enables construction of disaggregated system to improve resource utilization in order to deliver significant total cost of ownership and power efficient improvements in the data center. Now I would like to invite my colleague, Chris Peterson from Facebook, to talk about how CXL addresses the memory challenges in the compute landscape.
Thank you, Dipendra. Let's start by taking a closer look at some of the memory-related challenges that we're facing. Over the past 9 years, CPU performance has steadily increased with each CPU generation, with a lot of that improvement driven by CPU core count increases. Core count, the gray line here, has more than tripled in this time frame. At the same time, the memory bandwidth per channel has not kept pace and has only doubled. As a result, the bandwidth per channel that is available per core has decreased over time, as shown here by the blue line. We do need to keep those CPU cores fed, however, so we have to scale memory bandwidth in other ways. The side effect is that we need to add more memory channels, and we've gone from 4 to 6 to 8 channels and so on over time. Finally, more cores also means more memory capacity is required per server. The challenge with increasing memory capacity is twofold. First, it's becoming increasingly difficult to increase the density of DRAM due to scaling challenges, which means it takes longer to increase. Also, the price per gigabit has flattened on average in recent years. The implication of this is the second challenge, as memory is becoming an increasingly large portion of a server's cost and power consumption. This negatively affects the system and rack-level TCOs, or total cost of ownership, and this is incredibly important for many of us, especially at the hyperscaler levels. Finally, as memory speed increases, we can also install less DIMMs per channel, which further limits system capacity. Now that we've covered some trends for the memory technology itself, let's focus on applications. Earlier, we talked about the rapid growth in AI. Now let's look at this a little more closely. Our projections show that for some machine learning models, we expect to see up to 50x growth over the next 5 years alone. As we need to retain these models close to the compute that needs to operate on them, this is putting tremendous pressure on memory subsystem designs for future servers and requires us to rethink the memory hierarchy. Finally, let's explore the implications of these trends to server system designs. Earlier, I mentioned the trend to add more memory channels. This is becoming extremely expensive to implement. Each memory channel adds over 200 signals to the CPU package, the socket, and the motherboard. That means we have to add more layers to the motherboard, which in turn make the boards thicker. Also, as we're trying to increase the memory channel speeds at the same time, we need to use higher quality PCB materials. And with thicker boards, we often also have to implement backdrilling as well. More channels and more pins also makes sockets larger, which increases the motherboard dimensions, and which then decreases rack density as a side effect. And it also impacts the reliability of the system in general. I mentioned evolving the memory hierarchy. What this means is that we need to look at different memory types with different characteristics. The result is that we need to build more heterogeneous subsystems. The DDR interface and a DIMM slot are not well suited to these new technologies, and so we need a different, more flexible way to enable these new configurations. The good news is that we have a new interface that will help us address these memory and system design challenges, namely CXL. CXL memory can be different media types, have different characteristics, and run at different speeds, but still uses one common interface to the system. That makes system design much simpler. For example, we could design a system that uses both DDR5 and DDR4 memory on the same platform. Or we could use persistent memory in addition to those. This enables heterogeneity, which we need to continue to efficiently scale memory bandwidth and memory capacity. CXL is also about 1/4 the number of signals of DDR and can be placed farther from the CPU, which allows us to optimize our system designs further and better work around some of the system challenges that I mentioned previously. While all of this is very exciting to talk about for new technologies, it's even more exciting to actually see it implemented in hardware. So let's take a look.
Hello and welcome to the Facebook Labs in Sunnyvale, California. My name is Chris Peterson. I'm a hardware system technologist at Facebook. Today I'm going to walk you guys through our proof of concept for a CXL memory subsystem. So we'll start with the motherboard itself. So we have our next generation motherboard design here. The CPU here is an Intel pre-production Sapphire Rapid CPU. And alongside the CPU are the DDR5 DIMMs. For the CXL component, we have designed it such that it fits into a standard PCIe Chem slot. And on this card, we have an Intel pre-production FPGA. On this side, we have a by 16 CXL 1.1 interface. And on the other side, we have two DDR4 memory controllers. Each of those memory controllers is connected to one standard DDR4 register DIMM. And so we have a total of two DIMMs, each of which is 32 gigabytes, for a total capacity of 64 gigabytes behind the CXL memory. The other thing that we have implemented on the FPGA is a CXL 2.0 device interface. This provides us with a management interface so that we can do monitoring, firmware updates, or collect things like errors. So as an example, if we want to know about errors that are happening on the DIMMs, for example, for the media itself, if we want to look at correctable or uncorrectable ECC errors, we can use the device interface to help us collect those errors using the standard CXL management driver. All right, now let's boot the system. So let me walk you through what happens as the system comes up. So as the system firmware comes up, it will recognize that there's a device installed. It will train the link after the link has come up and trained at the correct speed. In this case, Gen 5 or 32 gigatransfers per second. The system firmware will then recognize that it's a CXL device instead of a PCIe device. So because it could recognize either one, it depends on the device that's been installed. In this case, of course, it's going to come up as a CXL device. It'll enumerate, and then system firmware will map it in as the CXL memory device into system memory. So now let's take a look to see that the system has come up and see if it came up at the correct link speed and link width. Okay, so now we're back up in Linux, and the system is booted and correctly identified the CXL device. So we can see that the CXL device shows up here in LSPCI. Further down, we can see that it has correctly identified as a CXL device, and the DVSec registers have been correctly mapped. So we can see CXL capability, CXL control, and CXL status, for example. And then finally, we can see that the kernel has correctly associated the driver for the CXL device, and it's now mapped accordingly. Now that the card has been correctly enumerated and mapped, let's take a look at how it actually gets mapped into system memory. So if we look at the NUMA-ACTL output here, we see that we have in a total of 3 nodes. 2 of them are the CPUs with their associated CPU cores enumerated and the local DDR5 memory. And then finally, node 2 here, as you can see, there are no CPUs because this is a CXL device. And there is 64 gigabytes of memory. Remember, this is what we had installed on the card, so everything is mapped correctly. And the CXL device is now mapped as NUMA node 2. All right, now let's run a test on the memory itself. Make sure it's working the way we expect it to. Here we can see that we've run a number of tests on the memory itself, a variety of different kinds. And we can see at the bottom here that the test successfully passed, which means the memory is working as we expect it to work. Now that we have the system up and running and the memory is tested, we're ready to do a lot more extensive testing. So thank you very much for joining us today for our quick demonstration.
Now that we've gotten a sneak peek at some CXL hardware, I'll hand it back to Dipendra to tell us more about where we can take CXL from here.
Thank you, Chris. Wow, that was a pretty impressive demo. It's always good to see the technologies that you're working on show up in real life and kicking and alive and well. Now let's look into some of the applications of CXL in the memory and storage segments. As Chris discussed before, one can envision a common platform as shown on the right here, where CXL can be used to provide additional DRAM bandwidth and capacity. Thus, one can basically decouple the compute from the traditional DIMM memory bandwidth and capacity. CXL offers the bandwidth scaling with width and frequency, as Chris talked about. Unlike traditional DIMMs, one can allocate different bandwidth with the same capacity by changing the link width, for example. PCI Express data rates, which are used by CXL, they are doubling every 2 to 3 years. while staying within the power, performance, channel reach, and cost profile, which is tremendous. For example, today one can get 32 gigabytes per second per direction with a by 8 at 32 gig. When we double the data rate to 64 gig, that bandwidth will double. That's a lot of pin efficient bandwidth with the best power efficiency that the industry has to offer. So we do get to higher latency with CXL than a local DRAM access. That's a given. Now that's inherent in any SerDes type of interface versus a parallel bus interface. However, as we said earlier, CXL accesses are similar in the latency characteristics to that of a remote CPU socket connected through UPI in an SMP system where NUMA domains have been very well established and proven to really work. So the question is, in my mind, is how much of memory stays with the traditional DIMM and how much of it migrates to CXL, and it is going to vary over time. With time, I can see that more and more memory will migrate to CXL because of these capabilities that CXL offers. And I can envision a system in the future where you have some memory that is completely on package and the rest of the off package memory is all connected through CXL as shown on the right hand side of the picture here. Basically, one can envision to even have a memory hierarchy where the on-package memory acts like a memory side cache or even a level 4 cache. So different things are really possible. CXL opens up the door for a lot of innovations. Backward compatibility, ensuring interoperability, unlike the DDR world, is something that CXL provides, and that offers really a compelling interconnect for memory to migrate to. It makes perfect sense for me that NVDIMM moves to CXL. As shown in the picture here, we can have storage class memory such as NAND to back up the DRAM hosted by the CXL device, which provides the non-volatile characteristics. One can even envision deploying a DMA engine to move the data from other DIMM slots into this NAND storage. The advantage is this is going to be hot pluggable, hence serviceable. And it can also be multi-headed and connected to multiple hosts for failover access. And we do not have to consume a precious DIMM slot, and we are not constrained by the form factor or power constraints. So these are huge benefits for the non-volatile memory to really migrate into CXL. Persistent memory regions behind CXL, they are now cacheable. All of this while we maintain the hot plug serviceability and multi-headed accesses for availability. One can even build very large capacity memory by having a DRAM as the memory side cache and have the entire large chunk of storage class memory be mapped into the cacheable system memory space. And we can use things like a HMAT table and interleave it accordingly. The CXL devices in both these types of memory can be augmented with DMA engines for efficiently moving the data and deploy the accelerator for local processing of data, as we will see in the next slide. One of the compelling new use cases for CXL can be that of computational storage. Imagine putting an accelerator in front of memory for near memory compute. Functions such as compression, encryption, computation for reliability like RAID 5, RAID 6, compaction for key value store, search engine, or vector processing for AI and ML kind of applications, all of those can be done there. DMA engines can be deployed to move data back and forth to wherever it is needed next. And best of all, we still get to use the standard drivers and management framework that we have developed over the years in PCI Express. One can also envision where the storage class memory can be mapped into the coherent memory space and have a local DRAM act as the cache and use some sort of smart analytics to prefetch the data from the storage class memory into the DRAM for improved latency as well as pre-processing of the data. And the picture on the right shows a very efficient system where these kind of capabilities can be combined with memory capacity and memory bandwidth expansion that are offered by CXL. What's important here is everything in CXL can be located even behind a low latency switch and be pooled across multiple clusters in a rack. So direct connectivity, pooled connectivity with all of these innovations, these are all possible. The bottom line is that with a simple set of caching and memory semantics enhancements on top of PCI Express and the ability to pool across multiple nodes, CXL enables one to build on top of the existing PCIe infrastructure and servers and offers a very effective and compelling interconnect to migrate to. It enables systems to scale with heterogeneous processing and memory with shared cacheable memory space that is accessible by using the same mechanisms that the CPUs use today. So, in summary, CXL is well established and it's an open interconnect slot. Tremendous involvement in across the entire ecosystem. The consortium is very active. I think close to 170 members. We are working on the third generation of the specification now. Lots of innovations happening in this space, and there is a lot of ecosystem support. You saw the demo that Chris showed. There is plenty of IP available, validation IP available, right? You got our platforms, you got the FPGA to do POCs on, and in summary, CXL is poised to be a game changer. Thank you all very much.